Okay, so this is chapter 3, and I think I've answered all the questions on chapter 2 on e-learning. There are not many questions, but there are some questions that I've tried to answer. So if you need more explanation, you should ask me either in the WhatsApp group or on e-learning discussion forum. Okay. So I hope you have watched the video on chapter 3. Okay, so and also I have provided the slides, and I really hope you have read the slides. Okay, so basically, if you look at the slides, and I hope you can see my screen showing the slides now, from page 2 up to maybe, I don't know, page 12. It's all about, it's just explanation, right? We can't even call this theory. It's just explanation up to question up to slide number 15 even, and then starting from slide 16, then we have talked about we discussed the quad rotor. So in chapter 3, the core topic is the quad rotor. Okay, so we have discussed in the video, or I have explained the mathematical model, right, of quad rotor, and also the controller part. Okay, so let me briefly overview what you have watched in the video and probably what you have read on the slides, right? So this is a simple figure showing the quad rotor. So quad rotor has 4 rotors or propellers. Okay, so this symbol, this depicts the angular speed of the propeller's rotation, right? And the rotation will generate thrust, as we can see here, T1, T2, T3, T4, and the propeller's rotation will also generate something that we call aerodynamic drag. Okay, so what lifts the quad rotor is due to this actuation. So the total thrust that acts on the quad rotor's center of mass is T1 plus T2 plus T3 plus T4. Okay, and if you look closely, the direction of the rotation of the propellers is different, right? So omega 1 and omega 3 rotates, if you look from above, it rotates counterclockwise, and omega 2 and omega 4 it rotates clockwise. Okay, and there's a reason why that's the case. So furthermore, if we want to generate so rotation of the quad rotor about x-axis is called the roll, or rolling motion. Okay, and the rotation of the quad rotor about y-axis is called the pitching, right? Pitching motion. And then rotation about the z-axis is called yaw, Y-A-W. Okay, so roll, pitch, and yaw. So if you want to have a rolling motion, from this figure you can see that if T4 is greater than T2, there will be a rolling motion, right? Positive rolling motion, right? Because positive is clockwise, looking in the direction of x-axis. And if you want a pitching motion, then T1 has to be greater than T3. Okay, and similarly, if you want yaw motion, T1 plus T3 has to be greater than T2 plus T4. Okay, it's not that, it's not T, but it's the omega, right? For yaw is different. For yawing, yaw motion, omega 1 plus omega 3 has to be greater than omega 2 plus omega 4. Okay, well, you can see this clearly by looking at this equation. So this is the equation for each individual thrust, right? So T1 equals to B multiplied omega 1 squared. So the faster is the rotation of propeller 1, the higher is the value of thrust 1. Okay, and there are two main equations that governs the motion of any rigid body. Okay, so but in particular this quad rotor, we have one is what we call the translational dynamics. So this is the linear motion. All right, so you can imagine if you want an object move in a straight line or move in a line in general. So this is the equation that governs that motion, right? So for our quad rotor, and this is gravity, which acts always downwards, right? It pulls the object downwards. And this is rotational matrix, okay, rotation matrix that we have seen in the previous chapter. This is thrust. This is T equals to T1 plus T2 plus T3 plus T4. What is B? B is the aerodynamic friction. So anything that moves forward, there'll be an opposing motion, right? Given the air. So any as long as you're on the earth, when you move, you have to go against the air resistance. So this is the aerodynamic friction. Okay, so this is the translation dynamics, and the other one is the rotational dynamics. So this equation, right? This is the rotational dynamics. This governs the rotational motion of a rigid body, or our quad rotor in this case. So here omega is the angular velocity vector, J is the inertia matrix, tau is tau x, tau y, tau z. So what is tau x? Tau x is given by this. Okay, so if the faster is the rotation of propeller 4 compared to propeller 2, you will generate a positive torque, which means your quad rotor will rotate in the positive rolling motion. Okay, and we have the equation for tau y, and this is tau z. So as I said earlier, tau z will cause the yaw motion, right? Next, what else? And then if you rearrange the equation, some of the equations that provided earlier, you will come up with this matrix equation, right? And this matrix equation is useful when you want to find the rotor speeds that are required to apply a specified thrust and moment tau. So in order to generate a specific values of thrust and moment or torque, you can compute what is the required angular speed of the propellers. So because at the end of the day is the angular is the propeller that generates the force and the torque. Okay, so this is a Simulink model. Okay, like I've explained in the video. In order to have this, you have to download and install the robotics toolbox. Okay, so if you download that properly, you should have this block in your MATLAB, and you can run it. And in the video, I've run the simulation, right? And you saw a quad rotor moving. So this is important to understand how can we control our quad rotor. So in particular, we have here, this is the loop Well, before that, let's look at the plant, right? So this is our plant, the system. And then we have, these are the set points. This is X and Y set points. This is the Z set point. So X, Y, Z are the position set point. And then this is the yaw angle set point. Okay, and all this 1, 2, 3, 4, this is in the world coordinate frame or the inertial coordinate frame. So here we have a position controller, this is velocity controller, and this is attitude controller. So attitude here refers to the roll and the pitch angle, right? Two angular values, right? And finally, it goes to the control mixer. So the control mixer is this equation right here. So the output of the control mixer is omega. Okay, and this is just the measurement. Anyway, so we have a yaw controller as well. So 1, 2, 3, 4, 5. So we have a yaw controller to control the yaw angle, and then we have the height controller, okay, or the altitude controller. So attitude, altitude, they are two different variables, two different controllers. So one thing that is interesting, I've explained in the video, is this controller structure, right? So this is what we call a cascade or a nested control structure. So normally in a control system, let me see if I can draw briefly here. So normally in a controller structure, in a controller block, right? Oh, it's too thick. Anyway, you have a singular block, right? So let's say this is your plant, or your system. Sorry, it's too thick. Okay, and this is your controller. This is the output, and you would have a feedback, right? And the feedback is compared with the set point, and then the error goes to your controller, and so on. But in our case, so the error goes to the controller. The controller will generate a control signal, right? Or sometimes we call it control input. Sometimes people call it control output. But mostly it's either control signal or control input. And this is what goes to the system. But if you notice here, the output of one controller becomes the set point to the next controller. Okay, so this is the position controller. The output of it becomes the velocity set point, and the output of the velocity controller becomes the attitude set point, and finally the attitude controller generates torque, tau x and tau y. So you should have or should be exploring this in your own time, right? In your computer, in your Simulink model. The equations for these controllers are given here. So this is the position controller, and this is the what is this? Velocity controller, because we are minimizing the velocity error. Vx, Vy as well. So there should be 2, right? But it's only shown here 1, but in the block there should be 2, Vx, Vy. This is the attitude controller, and again it's only shown for pitch angle. That should be for roll angle as well. We had your controller equation is not given in the slides, but you can look in the Simulink model. And this is the attitude controller, all right, to minimize the height of the quad rotor. And then the last slide, it talks about what the overview, the overall operation, right? So what it says is that we start with the position error. So let's say, let's say you want the quad rotor to go from one position to another in the world coordinate frame. First of all, you have an error, right? Position error. And in order to make the quad rotor to move from one place to another, you have to turn it, right? You have to rotate the quad rotor either in a rolling motion or a pitching motion, so that there will be a component of thrust in that direction. And in order to rotate your quad rotor, you need to have torque, right? You need to have pitching torque or rolling torque. And then finally, in order to have the torque, you have to make sure the propellers are rotating at certain speeds. So you see, just to move the quad rotor from one position to another, you have to do all these operations. So that's why we had to use the nested control structure. And the reason why this is happening, or this is needed, is because the configuration space of our quad rotor is 6-dimensional configuration space. So you can imagine your quad rotor as an object. You can place it in any position, X, Y, Z, and you can probably rotate it in about any axis, right? You can rotate in X, Y, or Z. So 6-dimensional configuration space. However, we only have 4 actuators, which are given by the rotors or the propellers. So this system is an example, a classic example of what we call an under-actuated system. And that is why, in order to make it move linearly or in a linear dimension, we need to use the rotation as our means to control. Okay, Jerry says this voice is lagging. I'm not sure why. Anyway, I'm recording this, so I will upload this on e-learning shortly. Okay, so that's all from me, an overview. For the detailed explanation, I've explained in the video. So do you have any question for me? Any question? Anyone? No. So Chia Ching Seng says no. Have you all looked at the tutorial questions? Any question on that? Okay. Pua asked me privately. Not yet. Jerry says not yet. Try tutorial. So not sure. Okay, it's okay. It's not super urgent for you to try tutorial now, because I think we are going slightly fast. Chia says haven't gone through all. Okay, good. Okay, let's Pua asked me a question. Sir, can I know how to derive or explain the tau, which is b dt t4 minus dt1. Okay, what does it mean? How to explain the tau, how to derive or how to explain. So this one, I think. So Pua asked me a question here. He says, how to explain this? Okay, how to explain that, right? Let's look at, let me open my sketchbook. So let's copy this, right? And then paste it there so that I can explain maybe better. Alright, so this is our figure. Okay, so the question for what is the equation for tau x is dt4 multiplied dt minus dt2, right? So tau x is dt4 minus dt2, right? So what is t4? This is t4, right? So t4 is given by, so t2 is given by, I think it's b omega 2 squared, is it? b for aerodynamic constant, right? Yeah, b omega squared, right? B is a lift constant. So just want to check. Can you guys hear me? Can you guys see my screen that I'm drawing? I'm writing something. Can. Okay. All right. Good. Thank you. Then T4, thrust number 4, which is this one. Whereas this one is b omega 4 squared. So first of all, if we look at these two, the faster the propeller rotates, the higher is the thrust, which makes sense, right? If you imagine if you have a helicopter, the faster you move the propellers, the more air you will push downwards, right? Air mass. So air mass you push downwards, and according to the Newton's law, for every action there's an equal but opposite reaction, right? So if you push something down, something will go up. Okay, so here, so there we go, right? So the faster is the omega 2, the higher is T2, and the same thing with T4. So so this is thrust, this is the force over here, but we want to compute torque, right? Torque or moment. And the equation for moment is if we have an object like this, what is torque? And let's say this is the fixed point. If you want to compute the torque, tau, you have a force here, right? So force is a linear motion, isn't it? If you apply force, an object will move in a linear fashion. Okay, but torque is what we call the rotational force. So in order to rotate an object, you have to apply torque. Okay, and torque is equivalent. The equation is force multiplied the distance from the distance of the lever, we call it, right? So force multiply the distance to the point, the fixed point, that is equivalent to torque. So that is why we have d So this is d, right? To the center of mass, dt4 minus dt2. So you might ask, why center of mass? Because by definition, center of mass is the point where, as if all the forces and torques act on. Okay, and there's a way to compute that. So let's look at T4 and T2. This is T4, this is T2. So we have to ask ourselves, what is positive torque, right? From the previous chapter. So that is why chapter 2 is very important. Okay, make sure you super understand chapter 2. All right, or uber understand. Anyway, so what is positive torque? Or before that, what is positive rotation, right? In x direction. Positive rotation in about x-axis is what? Is clockwise, isn't it? If you have your eyes behind, this is your eyes, okay? I don't know what is this. So this is your eyes looking in the direction of x-axis. Positive motion is clockwise. Okay, so that is your positive torque. Positive torque. If you give a positive torque, you will generate a positive rotational motion. So in order to generate positive torque, this has to be greater than this. Okay, so that is why we have a dt4 minus dt2. Okay. So if T4 is equivalent to T2, the torque is 0. There's no rotation. Okay. If T4 is greater than T2, you have a positive value here. And from the figure, you can see if T4 is greater than T2, you have a positive rotation. And then if T2 is greater than T4, this value will be negative, and from the figure you can see when that happens, you will have a negative rotation. Okay, so that's all. I hope you understand. What is that? Okay. All right, Pua says okay, understand. All right, so any other question, or else we can stop, because I've explained enough. Doctor, start from page 24. And then what? What is the question? I don't know how to use the rest of the formula. I've just explained to you, right? I've just explained. These are the controller equations. This is the position controller equation. So as you can see, this is desired position. This is actual position. We compute the error. Error goes to the controller. In this case, it's just a proportional controller. The output of positional controller, which is this one, goes to, it becomes the set point of the velocity controller. And then the output of the velocity controller, it goes as a set point to the attitude controller. And then the output of the attitude controller goes to the control mixer. The output of control mixer, what is control mixer? This is control mixer, right? The output of controller mixer is omega. So omega goes to quad rotor. So this equation is to compute, this is a controller equation. So given, for example, given a desired, let's start with this, given a desired position, you have to compare with the actual position, and then you can generate error, and this is the control output, right? Control signal. Okay. Anything else? Yeah? Huh? Yeah. Are you running or something? Yeah. No, I've explained already. Prime, B prime, B star. Which one? This one, V you mean? Did you understand what I've just explained? When did you join this class, Wong? What time you joined this class? Today? From the beginning? So you did not understand anything? What is that you don't understand? I asked you a question. What is that you don't understand, Wong? Wong? What? No, you tell me, Wong. I'm the lecturer, right? So you have a problem, you ask me. What is the problem? No, first of all, I don't understand what's the question. I think he wants to know how to apply the formula, for example, in a calculation. Okay, see, this is a straightforward question. You see, simple. Now I understand what's the question. So it says, so first of all, you have to understand what is V prime zero. Wong, do you understand what is V prime zero? What? Desired velocity in what coordinate frame? In world coordinate frame, exactly, right? So this is desired velocity in world coordinate frame, correct? So this is a rotational matrix, right? Rotation matrix. This rotation matrix maps from um, world coordinate frame to B prime coordinate frame. So this one is the desired velocity in B prime coordinate frame. So do you know what is B prime coordinate frame, Wong? Only one yes. So what is B prime coordinate frame? Wong? What is B prime coordinate frame? No idea? B prime coordinate frame is vehicle z axis. Seriously? Does that even remotely make sense to you? B prime is the coordinate frame, okay? And I've explained in the video. Let me see if I can open it. So we have B coordinate frame, we have B prime coordinate frame. Yeah, here, right? So if we look at the slides, so this is coordinate frame B. So coordinate frame B is fixed on the quad rotor, right? For example, if quad rotor is tilting forward, so the x-axis will be downwards, right? Because it's fixed on the quad rotor. So, but in order to do the control, we need to have another coordinate frame, which is B prime. So this is B prime coordinate frame. This is X B prime. This is Z B prime. But this is coordinate frame B, and this is coordinate B prime. So coordinate frame B prime is always no, it's a coordinate frame, right? So you cannot say parallel to Z axis. So it's always parallel to the world coordinate frame. Okay. At least the xy plane of B prime is parallel to the world xy plane. Is always pointing. So xb prime is always at the horizon, right? Or in other words. So this is B prime. So that's what we did here. We mapped from world coordinate frame to B prime coordinate frame. So now if you want a sample calculation, because this is the controller equation, right? So if you want a sample, then you need to know desired. Well, if you run the simulation and if you investigate what is inside here, then you can have your own sample, right? For example, if you know the desired position, this is the actual position which is measured, the feedback, and if you know Kp, in this case Kp is 1, then you have this. For this one, you need to get it from here. See, this is the rotational matrix. But however, rotation matrix is a function of theta. So for different configuration of the quad rotor while flying, so this matrix will be different. So if you want a sample, then you have to get it from here. Because I don't know what is the rotation matrix. It has to be taken from here, and it's a function of yaw, as you can see here. Okay. Okay, guys. Any other question? So please look at the tutorial. And in the tutorial, I don't think I gave you a question on the sample, because it's just arithmetic. Why would I? I don't think it's important to be able to compute this in terms of numbers, because it's just mathematics. You minus, you multiply, anyone can do that. And we have learned this to compute this in the chapter 2. So for this chapter, it's all about understanding the controller structure, why we do things like this, and so on. All right. Anything else? Okay, I don't think we have any more questions. So that's all for today. If you happen to have more questions, please you can either ask me in the WhatsApp group, or you can post it on the e-learning discussion forum. All right. Thank you.